So good morning. Here are the problems for alternating current circuits. Question number 1 talks about an air-filled cylindrical inductor, has 2800 turns. It is 2.5 centimeters in diameter, 28.2 centimeters long. So the length is given, the radius is there, the number of turns is there. What is its inductance? It's a direct formula that I've given you to find the inductance of a solenoid, isn't it? And then it says how many turns would you need to generate the same inductance if the core were iron-filled instead, and the magnetic permeability of iron is about 1200 times that of free space. So that's a direct question. Okay, there it is. The formula is B is mu naught Ni, basically for a solenoid. But then again, phi B is BA. I know I've given you the direct formula, but I'm trying to derive it again. So phi B, magnetic flux is B times A, which is mu naught Ni by the length. And finally, we end up with this formula, that self-inductance is mu naught N squared A by the length. Does the self-inductance depend on the current? The answer is always no. The self-inductance only depends on the geometry of it, isn't it? The number of turns, the area, and its length. And when you substitute mu naught, it's 4 pi times 10 to the negative 7. The number of turns is 2800, so that is squared. The area of cross-section is pi r squared, which is pi times the radius squared. The radius is 0.0125 in meters, divided by the length is 0.217. When you substitute all that, you get 0.022 Henry, which is the answer to the A part. A direct substitution of quantities. In the B part, you're asked to find the number of turns. So again, start with the formula. Make the number of turns the subject. You're going to have square root of what? That's a mistake there, isn't it? I don't know. Okay, go with the numbers that you have in the problem, or change the numbers. It's supposed to be 0.282, isn't it? Okay, that's going to keep happening for all these problems, I think. I'll try. Oh, I did change it. Okay. So again, with the numbers that I have, it's 0.217 by area is 1200. 4 pi times 10 to the negative 7. It's mu naught is actually 1200 times 4 pi times 10 to the negative 7, isn't it? Because the permeability of iron is 1200 times that of air. Is that clear enough? So for free space, it's 4 pi times 10 to the negative 7. For iron, it would be 1200 times that. That's why you see that 1200 there. So you only need 81 turns if you're using my numbers. So we are on to the second one. It takes 2.56 milliseconds for the current in an LR circuit to increase from 0 to 0.75 of its maximum value. That means it goes to 75% of its maximum value. Find the time constant. What is the formula for time constant of an LR circuit? Yes, inductance divided by resistance, that's all. So you're given the inductance, but you do not have the resistance, so you cannot find it that way, can you? Time constant is L divided by R, but you're asked to find the resistance of the circuit, so how do you do it? You cannot do it that way. So you'll have to go to the original formula for, is the current growing or decaying?
Growing.
increasing, so it's growing. What's the formula for growth of current? I is I naught e raised to minus t r by L. Okay, if you do not know the equations, it's very difficult. So you go for I is equal to I naught. Because it's growing, it's 1 minus e raised to. The equation that I gave you was for the decay. 1 minus e raised to minus t by tau. Tau is the time constant there, okay? And just the math there, 1 minus I by I naught. We are used to this when we did the CR circuits. So I'm not spending too much time there. The I naughts get cancelled. 1 minus 0.75 is 0.25. Then you know how to change the exponential into natural log on the other side. There I get 4 by flipping both sides, taking the reciprocal on both sides, and then the time constant is t by natural log of 4, which is 2.56 by natural log of 4. T is 2.56 milliseconds, and we get 1.85 milliseconds. Doesn't the problem say that it takes 2.56 milliseconds? That's what we're using. B part. Find the resistance, which is simple now. Now that you have the time constant, you know time constant is inductance divided by resistance. So rearrange, get the resistance. So that's in millihenry. And this is in milliseconds, so it doesn't matter. Both are in milli. It'll cancel out, and you get 16.8 ohm as your answer. That is question 3. Calculate the reactance of and RMS current in a 36 millihenry radio coil connected to a 250 volt 33.3 kilohertz line. Ignore the resistance. Wow. So that means there's only inductance. Isn't it? There's only inductance. How do you find the inductive reactance? Just now we talked about it. XL is 2 pi F times the inductance. Can't be easier than this. Don't expect anything easier than this. But do not forget to change kilohertz into hertz. That's the 10 to the 3. Millihenry into henries. So you got to divide by 1,000. That's how you get. Do you see the inductive reactance? The magnitude is so big. Why? Why? Because the frequency is high. Don't you remember that as the frequency increases, the inductive reactance also increases? Naturally, because it's multiplied by the frequency. That's why it's so huge. 7,532 ohms. Okay, and how do you find the RMS current? Simple Ohm's law. Voltage is current multiplied by reactance. Rearrange to get the current. This RMS voltage divided by reactance gives you RMS current. 0.0332 ampere. What is the reactance of a well-insulated 0.086 microfarad capacitor connected to a 22 kilovolt? That's the RMS voltage, 660 hertz line. And what will be the frequency and peak value of the current? Capacitive reactance, XC, is given by 1 by 2 pi FC. 1 by 2 pi FC, frequency given, capacitance given. So, microfarad is 10 to the minus 6, but it's 0.086, that's why it's 10 to the negative 8. So you get 2,804 ohms, and the RMS current is again VRMS by XC, which is 22 kilovolt is 22,000 divided by 2,804, 7.85. But did you notice that you're asked to find the peak current? Okay. So you'll have to do square root 2 times the RMS current. Is 11 ampere at 660 hertz. What is the resistance of a coil if its impedance is 235 ohm and its reactance is 135 ohm? That's a good one. What is the resistance of a coil? You know that a coil has both inductance and resistance, right? Yeah? So, its impedance is given. Do you know the meaning of impedance?
Yeah.
Impedance is the vector sum of resistance and reactance. So, impedance is given, reactance is given, you have to find resistance. What do you do?
Just put it into the formula.
What? What? Yeah, I didn't say the sum. I said the vector sum.
235 equals square root.
Okay, you have to bring in that. What's the formula? Z is equal to square root. What is the essential formula for the whole LCR circuit? What is the formula for the whole LCR circuit? Impedance. Let's get that. Impedance Z is square root R squared plus XL minus XC, the whole square. Okay. This circuit does not contain a capacitance. So you can just treat this as 0. So whatever remains. So Z is square root R squared plus XL squared. Doesn't that make sense? Because there's no capacitance here. And then rearrange to make, what do we have to find? Resistance. So rearrange that. So you'll have to square both sides. Isn't it? Square both sides and separate the resistance. That's what you see here coming up. Okay. Remember that reactance is also measured in ohms. Okay. Square both sides, take XL squared to the left hand side and make R the subject, and you get Z squared minus XL squared. Square root of that gives you 192.35 ohm. Impedance is square root R squared plus XL minus XC whole squared. Yes, I did. Okay. So calculate them individually. XL is 2 pi times F times the L. Okay. Frequency is 10 kilohertz. That's why it's 10 to the 4. Inductance is in millihenry. And remember, it's 32 millihenry. That's why I put it as 3.2 times 10 to the negative 2. I get that. And then XC is 1 by 2 pi FC. Capacitance is 6,250 picofarad, which is 6.25 times 10 to the negative 9. And I get that as 2546.5 ohm. Then put it back into the formula for impedance. Resistance squared, resistance is in kilo ohms. You know that the negative there does not matter because when you square it, it's going to become positive. And I get 8,716.5 ohm. Your name is on YouTube. Okay, so tan phi is XL minus XC divided by resistance. So that's the advantage of calculating XL and XC individually. See that? So now you have XL and XC. All you got to do is just take the difference divided by the resistance. And here a negative matters, doesn't it? because you're going to get that negative. XC is greater than XL, and so tan phi is going to be negative. Then when you put it in your calculator, you're going to get tan inverse of that negative number. Make sure your calculators are in degrees. So you get negative 3.52 degrees. You know that negative there matters. It shows that it lags, isn't it? Because if it's positive, it leads. Negative lags. Okay, and then you also have to find the RMS current. That's just Ohm's law. Vrms by Z. Vrms is given as 725 divided by the impedance that you got. And that gives you 8.32 times 10 to the negative 2 ampere. Okay, an LRC circuit has inductance 4.15 millihenry, resistance 3.80 kilo ohm. What value must C have to produce resonance at 33 kilohertz? The formula for resonance, resonant frequency, F naught or FR, whatever, 1 by 2 pi square root. You have to be careful when you write that formula. Either write it that way, or it's 1 by 2 pi square root LC in the denominator. Is that clear enough? People make a mistake. So 1 by 2 pi and square root LC must be in the denominator with 2 pi. Either that way or this. Both are the same. Substitute. Square both sides. Rearrange. Get C as the subject. Substitute. Plug in the numbers. Calculate properly. Get the answer. Inductance is in millihenries, so it's 10 to the negative 3. And the resonant frequency is in kilohertz, so again 10 to the positive 3 now. Get the capacitance as 5.60 times 10 to the negative 9 farad. At resonance, what happens at resonance? What about XL and XC at resonance? They become equal to each other. So they cancel out in the formula for impedance, they cancel out, isn't it? And so impedance becomes just equal to the resistance. Now can you tell me, is the impedance maximum or minimum at resonance? Impedance. Impedance is minimum because, just mathematically look at that, this whole term became 0. And impedance is equal to resistance. So impedance became minimum, which means the current becomes maximum. That's the idea. So therefore the current at resonance is maximum because this is a minimum value now. If you use the peak value for voltage, you get the peak value for current, naturally. What is given is the peak value for voltage. So you get 35.8 milliampere. Okay, so that is question 7. Can't get easier than this. Number 8. Let's look at it. Sometimes I shout with a purpose. A 35 millihenry inductor with, can't see that, it's 2 ohm resistance is connected in series to a 26 microfarad capacitor and a 60 hertz 45 volt source. Wait, is that 45 volt RMS voltage or is it the peak voltage? How do you know? Because I told you that if nothing is mentioned, then it is always the RMS. You need to remember that if nothing is mentioned, if you have a voltage given without saying whether it's RMS or peak, it's always RMS. For example, when you're asked what is the voltage on these lines, what will you say? 120, right? Is that RMS or peak? RMS. Yes. Know that. Okay, so you have to find the RMS current, the phase angle, and the power dissipator. Here we go. Find each one individually. Again, inductive reactance is 2 pi F times the inductance. Get smaller numbers now because the frequency is small. There you go, 13.19 ohm. XC, 1 by 2 pi FC. I have to fit all this onto that screen, so I'm writing small. 26 microfarad, that's why it's into 10 to the negative 6, gives 102 ohm. Impedance is simply square root R square plus XL minus XC whole square. Resistance is 2 ohms. That gives you 88.83 ohm for the impedance. And the RMS current is the RMS voltage by impedance. And what is given as the RMS voltage, so you just have to divide. You get 0.51 ampere. Again, the phase angle is XL minus XC divided by the resistance. Minus 44.4, take the inverse of that, tan inverse gives you negative 88.7 degree. Here that means the capacitance has an upper hand. It's taking it close to 90 degrees, isn't it? If it's only a capacitance, remember that it will lag by 90 degrees. Now it's lagging by 88.7. Power, RMS power is given by I squared RMS times the resistance. Isn't that the formula for power? I squared R. That's it. So you get 0.51 watts. An inductance coil draws 2.5 ampere DC when connected to a 45 volt battery. When connected to a 60 hertz 120 volt RMS source, the current drawn is 3.8 ampere. Determine the inductance and resistance of the coil. Good one.
I was worried you were going to tear down.
No.
Silly nose.
No. Okay, the resistance is voltage by current, because when you connect it to a DC source, the coil only behaves as a resistance, isn't it? Okay, that's what I said. So it's 18 ohms and then the Z. Impedance is Vrms by Irms. Vrms is 120. The RMS current is 3.8. So you got the Z. Now that you know the impedance and the resistance, definitely you can find out the inductive reactance using that. Is that the formula we have used a couple of times today? I have to separate the inductance and then substitute. Or you could have found out XL first and then put it equal to 2 pi F times the inductance. You could have done that. Try to do it in one step. I got 69 millihenry. Problem done. Thank you. If you like it, say that you like it, share it, spread the news so physics becomes all the more popular.